Hello, everybody, and welcome to practice number 7 of Circuit Lab. Who all do we have on right now? We may not have as many people as normally. Hello, Mr. Diazzi. How are you doing? You're one of our normal people. Hello, Sir Flim Flam. Good to have you as well. So we may not have as many people on today because I know it's the Thanksgiving holiday, but I also wanted to start off and let everybody know that all 15 practice sessions have now been uploaded. So I'm going to put that out here. Very good. Please make sure that you subscribe, and please let your friends know how to subscribe. Okay? So, with that, are there any questions on any of the practices we've had thus far or practice 7? How do you do a level 5 combination? Very good. Okay, well, what I'm going to do here is I'm going to switch over and we're going to go look at the homework generator. So if I go here to the homework generator, and I go over here to level 5. So if I look at level 5, remember, you always want to simplify the diagram, okay? So if I look here, I want to quickly combine things that are easy to combine. So looking at this, R1 and R2 are in parallel, and R3 and R4 are in parallel. So that's pretty easy to combine. The other thing is that you'll notice that R3 and R4 are the same value. So when I've got 2 in parallel with each other, they're the same value, that I don't even hardly need a calculator. I can just make that, take 1/2 of that, and that comes out to 161.5 for these two combined. And then these two are very close to each other, so it's going to be around 230 ohms combined. So it's 230 plus 116, and then those two will be in series, and so be about 390. Okay, so it's 223 and 161. So the R equivalent is 380. Okay, then what you'll notice you notice I combine these two, and then I combine these two, and you'll also notice that in the answer section I wrote down what you should do. And then these two are then added to those. So again, we combine the stuff that's easiest. Okay. Once I get the total R equivalent, I can figure out the I total very easily, because that would be equal to the V battery divided by the R equivalent. And then I just use current splitting for both of these. Now you'll notice that because R1 and R2 are very, very close in size, the split is almost equal. It's almost equal. But these two are exactly the same, so the split is exactly equal. So I3 and I4 will always be half of I total. And then you just multiply to figure out the voltages. Now, remember, you only have to solve for one voltage here and one voltage here because it's always going to be the same thing. The voltage across R1 is always going to be equal to the voltage across R2 because they're using the same nodes and they're in parallel. And the same for here. And then if I take these two numbers and add them together, they'll equal the V battery. And then I can either use V squared divided by R, I squared times R, or VI to calculate all the various powers. So Flim Flam, did that make sense? Okay, or Mr. Dazzy? Okay, can I explain the formulas for magnetic flux? Okay, very easily. Okay. So we're going to go to the slides. Da, da, da. Okay. So when we talked, we talked a lot about north and south poles, how to draw the lines, okay, and how Earth's magnetic fields work, the magnetic shapes. So let's talk about magnetic field current. Magnetic field current can be caused by moving charges, okay? So this is induction. So if I've got the current that's moving that way, the magnetic field goes around it sort of like in a disc, if you will. And so if the current's going that way, I put my thumb in the same direction as the current, and then with my right hand, move it around. And that's how the field lines go. Okay? So you'll notice that this looks a lot like sort of a circular magnet. Now, the way you can figure out what the magnetic field is that if you know the current, you multiply that by the permeability and you divide it by the circumference, that's where you get the magnetic flux, okay? Keep in mind that the permeability of free space is 4 pi times 10 to the minus 7 Tesla meters per amp, okay? Now, and what's going to end up happening is that this answer is going to come out in Teslas. Now, in most material that you come across will have a permeability that is different. And in fact, we go to the homework generator and we go all the way to material data sheets here. You'll notice, I will give you, hold a second, magnetic susceptibility and permeability. So here's the permeability of everything that you'll find, and here's the relative permeability. So this is what air is compared to the vacuum of space. And you'll notice to about 7 decimal places, it's 1. So always assume air has a relative permeability of mu sub 0. That's at 8.85, or excuse me, that 4 pi. But you'll notice here, like most things, have got very close to 1, okay? With the exception of ferrite, manganese, zinc, electrical steel, okay? Ferrite, okay, which is nickel, zinc. So you'll notice that a lot of your ferromagnetic materials here, okay, have got really, really high permeabilities, okay? And then you'll notice iron, you're looking at 5,000. And the more pure you make the iron, the better it is. So here it's like 200,000. So that's how we increase the magnetic field, just by changing the material that it's in. So think about the iron that's within the steel, or the zinc, or the nickel that's in the steel, sort of supercharging the magnetic field within it. Okay. Now, let's go back to the presentation. Okay, so that's for a straight line of current. Okay. Well, what happens if I put it around in a loop? If I put it around in a loop, I'm actually creating a magnet with a north and south pole. Okay. Because if you notice, the current goes here, goes down and around, and comes back out. And so when you put all those circular, you can see the circular magnetic field lines around, they all start to create a north and south pole, and it mimics an actual magnet, a permanent magnet. Now, what you'll notice here also, okay, is that if I follow the current around and with my hand and use my fingers around, my thumb will always point towards the North Pole. And so that's how I'm able to determine what's the induced North Pole. Once I know which one's the North Pole, the other one's the South Pole, and I can draw my magnetic field lines. And again, mu sub I divided by 2r. And you say, well, why is it 2r? Okay, and the reason why it's 2r is that we're no longer going around a single line, we're going around a loop. Okay, now let's say I put a bunch of loops together. All right, now at this point, the magnetic field lines are all concentrated. And each one of those loops, even though it's the same current going through here, okay, is adding current or adding magnetic flux, such that now B is now equal to mu Ni, where N is the number of turns per meter. I is the current, and mu is whatever type of material I happen to put in the middle here. So if I take, and let's just look at this. So the way that works is that let's say I take this wire and I make a whole bunch of loops. Okay. Oops. See, that's the loops. I put them together and I run a current through here. I'm going to make a solenoid or an electromagnet. Okay. Now look, it's got air in the middle. So the mu sub 0 is about the magnetic permeability. But if I take this piece of steel, which has got about 200 mu sub 0, and I put it in here, I just increased the magnetic ability of it 200 times. Okay. Now, the other thing is that the more turns I can give per inch or per meter, the stronger the magnetic field. So that's why you'll notice that they have thousands and thousands of windings. The other thing is that it doesn't currently have any current going through it, so it's not inducing a magnetic field. However, the more I increase, if I double the current, I just double the magnetic field. So you can well imagine it's a lot easier for me to get longer wire and put more windings on than it is for me to increase the current. And so they might put in 1,000 windings or 1,000 turns per meter, which all of a sudden now I've got 1,000 times the magnetic field. And that's a lot easier than bumping up the current 1,000 times. And then I put the metal in there, and depending on the metal I pick, it could be hundreds or thousands of times or tens of thousands of times more. So as you see, I can make a very powerful electromagnet without having to increase the current one bit. Are we going to have one of these sessions next Sunday? Yes, I am going to have one of these sessions next Sunday. Now, it may be from my sister's house in Houston. We'll just have to see. But I'm going to keep holding this because I know that the invitationals have started now. All right, Sir Flim Flam, did I answer all your questions about the formulas? Okay, good. And yes. Okay. Now, the reason why I went ahead and put all 15 up there is that sections or that practices 1 through 12 definitely cover all of Division B. And 13, 14, and 15 are really C only type topics. But some of the stuff with switches and such is really Division B level. They love to give you a couple of light switches and give you some three-way switches and see if you can wire up a three-way circuit. They love to give you different types of switches and see if you can identify whether they're single poles, double throw, what have you. How do we practice for the lab section? Very good question. Okay, so my recommendation for practicing for the lab section. If you have a hobby store, okay, and or your team has access to get a breadboard, get one. If you can get different types of resistors, get them. The most important thing for you to get, though, is a multimeter, okay? And you can buy them at Walmart. These are Harbor Freight. They're actually free with almost any purchase at Harbor Freight, or you can pay $7 and purchase one. But this is a great way to practice, and you should practice measuring resistance and voltage, okay? I would definitely try to create, if you will, electromagnets at home. And again, you can find a lot of stuff online for how to do that. I would also definitely try to create lemon, potato, and Coke batteries. Again, those are real popular. The most important thing I can tell you that will help with your hands-on is practice, practice, practice. Get used to using your multimeter and get used to figuring out how to take voltages and solve problems. In other words, they may give you a voltmeter, or they may say you can use your own, and they'll say try to figure out where the problem in the circuit is, and you try to figure out by the voltage which is where it's shorted out, maybe if the battery's dead, maybe if the switch is in the wrong position, etc. Should I have a chart with permeability of materials in my binder? Absolutely. You should also have a chart with dielectric. In fact, that's why I sort of made it the very first tab. Okay. So if you notice the first tab in the homework binder, okay, here we've got the permeativities. So for electric fields, this is really important. So when we get talking about capacitance, you know, just like an electric field, this is important. So what you'll notice is like glycerol and water really may have higher permeabilities than air and water. And, you know, air is very, very close. Okay. Whereas if you look over here, it's sort of the same way, but it's for magnetic materials. Okay. So I would include at least something like this. This is straight out of Wikipedia. You can get other ones. Okay. I would also include the resistivity and conductivities, as well as the temperature coefficients. Okay, so if they give you something and they say, okay, you've got iron, is iron a decent conductor? And it's not a bad conductor. It's not horrible. I mean, it's nothing like silver or copper, but it's not terrible. So iron actually conducts electrons very well, but it also has a big impact on magnetic permeability. Okay. Now, what you'll notice, though, is that the temperature coefficient is much higher here. So what that means is that the resistance increases faster for iron than it would for, let's say, copper. And you'll see because copper costs a certain amount, and it has such a low resistivity, that's why copper is the material of choice for most wires. Silver, of course, would give you better conduction, but it's only a small amount, and silver is just so much more expensive. And what's hilarious is that you always hear about gold. Gold is actually not as good as copper, okay? And of course, gold is much more expensive. Okay. Arvin D, other than circuit analysis, what else do we need to know about DC and AC circuits? Okay, if we go back to the rule book, okay, pretty much for DC circuits, you're going to need to know that's where you're going to do most of your circuit analysis. In AC circuits, you just have to know, and let's do a binder check. Who's ready for a binder check? All right. My question for the binder. In your binder, find the reason we transmit power over AC. using AC. Guys, Brandon, take your time, but definitely find your binder. This is only the first binder check. Okay, explain it, Mr. D. Everyone else, see if you can find it in your binder. This is one of the things I fully expect everybody's going to ask the question. The transmission losses are much less for AC. Okay, that is correct. So the transmission losses are much less over longer periods of time. Okay, and so what it is that DC usually has much higher losses for temperature. So the distances that you can transmit power are actually much shorter. So they would have needed more power stations, and you would have needed more wires to go to a house. So you wouldn't have been able to provide simply two conductor, well, actually it's 3 conductor wire to a house. And what they do is that they provide 3 conductors to your house that are AC, and the 2 conductors that are AC are 180 degrees out of phase. Okay, so while one's going up, the other one's going down. When you add them together, they cancel each other out. But here's the really neat part. When you are powering your house, most of your house is 110, 120 volts, right? So what ends up happening is that so most of the devices in your house are 110 volts in the United States, but that is using one of the hot wires and your ground. Okay, so when you compare it, it's 110 volts. However, let's say I use the one that's in phase and then the one that's exactly out of phase. Well, they're always 220 volts apart. See? And so that 220 I can use for things that need more power. So I've got a couple of really big energy using things in my house that run off of 220. Those are things like my air conditioning, the big fan, my washer usually is going to be your dryer. Your washer can normally run off 110, but my dryer is going to need 220. Okay. And there's going to be a couple of other appliances. And so these are usually things with very big oven, very good. That's why, believe it or not, I actually had a situation at my house when I lived in Ohio. This was the first house I had, and a rock had cut one of my 120 or 110 volt live wires to the house. Here's the weird part. Every light in the house worked. My TV worked. My oven did not work. My AC did not work. My heat did not work. None of the big stuff. My electric clothes dryer did not work. Okay? So what ends up happening, and so they had to replace the wire to the house. And then they also put in a protection to keep other rocks because it was a rock that had moved through there and cut that. Okay? That's right. Uses 220 because nominally in America, it's 110 volts is what most stuff runs off of. How do fuses work, and do modern houses have different kinds of fuses? Okay. Now this one is actually a little bit later. I think fuses are covered in number 12. Let's see if I can find it. Okay. So I'm going to go here to the menu. I'm going to the national website, Division B events, Circuit Lab. We come down here to, actually it's practice 11. Okay. And if I come here, and this is the one that covers switches, talks about single pole, single throw switches, single pole, double throw switches. These are the majority of the ones you'll find in your house. You'll find some of these others, but knowing how to be able to identify those switches is important. But let's talk about fuses. We wanted to talk about fuses. So right here is what fuses usually look like for the DC type of fuses. So sometimes they'll look like this. And what they have is they have a little filament inside of them that's rated for a given amperage. If you exceed that amperage, that little filament will burn. So if I look here, the little thing that looks like an S in here or looks like a little sine wave in here, that's thinner than the rest of it. And they'll put out here how much amperage it takes before this fuse burns. So this one here will be good for 4 amps, 3 amps, 15 amps, 40 amps. You'll notice the bigger the fuse, usually the larger the size, and definitely the larger the portion of the filament. And what it does is that if I tried to put 16 amps through here, or if I had a short and I tried to put a whole bunch of amperage through there, that filament is designed to burn lickety split. So it burns very, very quickly. So it protects my wire. So let's say I had a wire that was rated for 20 amps. I put a 15 amp fuse on it. I never have to worry about melting that wire. The problem is though, is that once it burns that fuse is done. It's gone forever. And so first you have to fix whatever caused the overcurrent situation. And then the second thing, you can replace the fuse. So these are the types that you see in cars quite a bit. Here's the type that you might see in an electronic appliance. And usually they make it clear at some portion so you can visually see that they're burnt. And here are the symbols that you might often see for a fuse on a circuit diagram. Now, you also have circuit breakers, which are like a switch, if you will, that automatically flips open. Okay, they automatically flip open or trip if you exceed the amount of amperage. So you'll notice that it's written on here, 32 amps, 20 amps, 8 amps, okay? Occasionally, they'll put two circuits together for like a 220 circuit. So in other words, each one of these is a 10-volt circuit, but they put them in a double pole, single throw. So what that means is that these two are actually two switches that are tied to each other. You'll see that a lot in your circuit breaker box for the stuff that's 220 in your house, okay? And what this does is that if I get more than 32 amps or if I stay at 32 amps for too long, this circuit will trip. And what's really nice about that, okay, is I fix the problem. I unplug some of the stuff, the excess stuff. Maybe I turn off all the big stuff that's going on in the house at the same time. But I don't have to go out and buy a new circuit breaker. Once I fix it, I flip it back in place. It's working great. Now, the key thing about a circuit breaker is that if you ever reset a circuit breaker and it trips immediately again, you didn't fix the problem. You got a short, you got an appliance that's trying to short out, you got something going wrong, okay? Don't try to force it to keep it in place because the safety mechanism is trying to tell you something, okay? Does that make sense? Oh, at your house, there was a lightning strike and a lot of your appliances got electrocuted. Did the energy get through the circuit breaker fuses somehow? Yes. Because if it struck the house, okay, depending on where it hit in the house, it may have hit on the appliance side of your circuit breaker, okay? The only way that your circuit breakers would have protected you had the lightning hit on the other side and it tried to go through the circuit breaker. But if it hits on the house side of the circuit breaker is not going to protect you at all, okay? So they actually have lightning arresters. That's why they recommend that if you've got some very expensive pieces of household equipment, that you have something with either a surge protection or a lightning protection, or they'll sometimes refer to it as lightning suppressors. Like this house here in Texas, they actually had one of the dishes up on top of the roof. Those things get struck a lot by lightning. Okay, it got struck by lightning, and since it was on the circuit breaker side, it blew out like the home media projector. It blew out the garage door opener. It blew out a lot of stuff that had to be replaced. Oh, why do rainstorms and heavy snows create a blackout, and what is a blackout? So blackout is when you lose power. Okay, so there are two main things that you'll hear a lot about from power companies: blackouts and brownouts. So a blackout is when you lose power. Now they could be caused by, a lot of times, a lightning strike hits a substation, hits a transmission pole, hits some other type of equipment that either eliminates the ability for them to step down, the power into your house, or somehow takes out the wires or some of the other equipment. So it could take out a transformer. It could take out the transformer that's on the pole right outside your house that does the final step down before it comes into your house, something like that. Another thing is that when it's raining, okay, in addition to lightning, a lot of times limbs and trees fall over from the rain and the wind. Well, when that happens, sometimes it knocks down the power lines, or it somehow, if a branch goes across it and the branch is really wet, it creates a short and it shorts it out. And believe it or not, all that electrical equipment that the power companies has, it all has fuses too. So when a short occurs, those fuses blow, which is great because it keeps the power lines from causing all sorts of problems. Okay. So that's why you'll see the power companies often cutting trees and cutting limbs around their power lines because they don't want the limbs to fall on top of them. And it really happens a lot with snow, and especially with ice, because snow and ice, they get really heavy and then the limbs crack or the tree falls over. Okay. Now, a brownout is normally occurs when the electric company can't produce enough power, okay, because there's something going on. Like, let's say we're having a heat wave. Okay, if we're having a heat wave, everybody's got their air conditioning cranked up, and everybody's air conditioning is struggling to keep up with it. And what ends up happening is that they can, things like air conditioning use up a lot of power, okay? So therefore, they can't quite create enough power, so their voltage starts to drop. And the reason why they call it a brownout is that a lot of stuff is still working. Some stuff that has a voltage threshold is not working. But more importantly, if you look at your normal light bulb starts getting dimmer and dimmer. That's why they call it a brownout. Your Xbox almost broke because of a brownout. So whenever you've got a brownout going on, turn off anything you absolutely don't need. Okay. And be ready, because brownouts often lead to blackouts. If you've got a blackout, or if you see a storm coming in, make sure that none of your electrical appliances are plugged in without being plugged into some sort of surge protector. And generally speaking, if you don't have to have it plugged in, don't. Okay, so that's when you'll see Mr. Burleson quite often. I'll unplug my laptop and I'll just be working with it wirelessly, because the electrical thing, the electricity won't come through the Wi-Fi. So then I'm pretty safe. However, generally speaking, don't be near windows. Don't be touching a lot of metal stuff, because if lightning does strike your house, you don't want to get hit by that. And there are people who die from lightning strikes. There are people who get injuries, whether it's burns. You can lose your hearing. You can lose your sight. Some people get struck by lightning and nothing happens to them. It's really sort of things. And sometimes when you get struck by lightning, I knew there was a kid in Ohio who got struck by lightning. He was playing basketball, and the lightning struck the basketball rim because it was connected through a metal pole to the ground. And it was just so close, he ended up getting electrified by it, and the poor kid ended up dying. Okay, any other questions? And by the way, this is open to all parts because I know lots of you have already gone through several practices ahead of time. Okay, has anybody done a sample test from scioli.org? Yes or no? I'm just doing a survey. Okay, I'd like for everybody to please go, and let me show you how you go there. So we're going to bring up, okay, so on the national website, they've got lots of really great things. But if I go up here and I type in scioli.org, okay, you will notice that you've got all the forums, all the build events, all the study events, etc. You've also got the test exchange. So if I go over here to test exchange and I go down here to Circuit Lab, okay, I've got a key, a sheet, and a test. So let's download the key here. And so it's got all the key and how they solved each of their problems, okay? If I go back here, so I print that out, right, of course. But if I want to, let's go and look at the test. And here's the test. It's a 13-page test, okay? And so you'll notice here, they've got 10 volts here, and they want you to find the voltage between nodes 1 and 2. So here's 1, and let's see, where is 2 and 2? All right, the voltage between nodes 1 and 2 is pretty easy. So it's between this node and this node. Who knows the answer? Write it in. You don't need a calculator. What is the voltage between nodes 1 and 2? Anyone? Well, can't see. Okay. Can you see now? Lighting's weird. Okay, is that better? I apologize for the lighting problems. So, what is the voltage between nodes 1 and 2 with a 10-volt battery right there? I may have actually given you the answer. 10 volts. Mr. Dazzy, that is correct. Because if I ask what the voltage is between here and here, by definition, since the battery is 10 volts, the difference between here and here is 10 volts. Okay? I don't need to know anything else. Now, between 2 and 4, this is a lot tougher. Okay? So at this point, I need to find out the equivalent resistance of this entire circuit. So what I would do here is I would add the ones that are in series that are easy to add. So this is 10 plus 20 plus 20. So that's 50 ohms. Okay? This one here is 10 plus 150, that's 160. Okay. Now I've got, in this case, I've got 160 in parallel with 50. Okay. So I do 50 in parallel with 160, and I come up with this resistance here. Okay. Now this resistance here, if you will, oh, wait. Yes. So this resistance here is now actually in series with this resistance. So I add it to that resistance, and then it's in parallel with this resistance, which is 10 ohms, okay? And I find the entire resistance from this node to this node. Now, from this node to this node, I know it's going to be less than 10 ohms, and I put it in series with 20 ohms. So the R equivalent, I know, will be more than 20, but less than 30, okay? Once I determine that, I can then determine the current that goes here. And because I know the various resistances, I can figure out how the current is then split. Once I know the current that goes through here, I know what the voltage is here, here, and here. and I can determine the voltage at 4. And if I assume that the voltage here is 2, and the voltage here, or excuse me, the voltage at 2 is 0, and the voltage here is 10 volts, I can easily then calculate the voltage here at 4. Okay? If I go back here to my handy dandy, okay? And so what you'll figure out is that, look, the overall resistance was 28.444, okay? Now, the cool part about that is that that makes sense because it's more than 20, but less than 30, which I knew it was going to be, okay? And so this one was easily 10 volts. This one ends up being about almost 8 volts, 7.9 volts. And you see how they calculated it, okay? You'll notice that this one actually had a lot of calculations in it. So my recommendation is draw and have lots of paper, okay? Now, you'll notice it said find the effective resistance of all the resistors, okay? Well, you actually had to have that to figure out the voltage. So I think that was actually sort of not very fair. So you had to solve for the 28.43 ohms or 44 ohms before they even asked the question. I would have actually asked that question first and had you go down there. And then it asks you, what's the current flowing through R1? Well, the current flowing through R1, if I look here, is the entire current of the entire system. So that is going to be the voltage, which is 10 volts, divided by the 28.44. Okay? Again, I would have asked these two questions earlier because we had to solve for those to get the other stuff. So believe it or not, sometimes, guys, these questions here are actually the tougher questions to ask. So look at this, because you would have had to solve for this before you answer these guys, okay? Color code R7, okay? So if I look here, R7 is 150 ohms, okay? Now, you guys may remember that number 10 is where we had the resistor color codes, okay? Or excuse me, practice number 9 was where we had the resistor color codes. So here's the color codes, but if you remember, I said there's sort of standard ones. So 15 is going to be brown and green, and then we have to say 150, so that'd be 50 times 10, so that'd be brown, green, brown, okay? And then, hold on a second. So 150 with 10% tolerance, and 10% tolerance would be silver, okay? So it is brown, green, brown, silver. And let's see if that's correct. Brown, green, brown, silver. Did that make sense? So my recommendation is download that test. See how you do. You're probably, the first time you're going to take that test, you're going to get like a 50% if you're lucky. Okay? That's great, because then it tells you what you need to work on. Then you use the key and you write out how you solve each one of those problems. That test and how you solved every one of those problems, that goes in your binder. If they ever reuse that question, you get a lazy event supervisor like this guy right here. I reuse questions. Now, I'll often change a couple of the values. So like I'll change that 150 ohms to 100 ohms. So you can't use the exact same answers, but you look at how you solve the problem. And then you do that exactly the same way again. So go down to Scioli, Go to the test exchange. Start downloading tests. Start downloading keys. Take some. Get together with your coach. Have your coach start giving you tests. Now's the time. You've studied enough stuff. Start taking some tests. And don't take tests all written by the same person, because you don't know who's going to write your test. And if you happen to know who's going to write your test, of course you want to get some of their old tests. They tend to have ways of doing things. Like, I'm an electrical engineer. I tend to write a test. People look at it and go, yeah, an electrical engineer wrote that. A really good friend of mine, Roger Demos, who is the national event supervisor for Circuit Lab along with me, guess what? He writes outstanding tests, but you look at it and you go, wow, that was written by a physics teacher. Okay. And they're outstanding tests. And so I'll often grab a lot of Roger's best questions, throw them on my tests. Why? Because I want to throw in some physics-based tests as well. Okay. Any other questions? But remember, some of the old tests as rules change. So I will tell everybody to always make sure that you download those tests, but at the same time, you try to not just rely on them totally. Okay. Now, any tips for the hands-on part? Again, try to recreate it. Okay. If you've got 4 or 5 people in your area, each of you come up with hands-on activities. Some of them are going to be simple, like a potato battery. Okay. Some of them are going to be very hard and will involve circuit boards. The key thing is, the more you can get hands-on stuff, the better off you'll be. Make sure that you know what the different types of switches look like, because guess what? They're going to put a lot of switches at you. Make sure you know how all the batteries work. Okay. Know how a telegraph works. That is correct. Know how an electric buzzer works. That's another common one. And both of those are based on electromagnets. Okay. And that's how they did the transmitting. Okay. Don't worry. You won't have to know Morse code, but you'll have to know how a telegraph works. Okay. And if you see one, be able to label the parts. Do I supervise any invitationals? I have. And I may be writing tests that may be used at various invitationals. I usually write for a couple of invitationals throughout the country. And then if they're local or what have you, I will go to those. I also write a couple of different state tests, and I also write some regional tests. Now, my general philosophy, I will write a test just like it's for a regional and an invitational, because giving somebody too easy of a test doesn't tell them what to study. So early on in the season, if I'm getting 70, 80% right on a test as a top score, I feel good, because that means I've given them a lot of information about what they need to study. At nationals, the teams are so well prepared at nationals, and they've had all year to prepare. Okay. The top teams, it's not uncommon for them to score in the 90s on one of my tests, even as tough as I can make it. Okay. They're still scoring in the 90s because they're able to split the test, and both kids are really, really sharp, and both kids know all their stuff. They're getting all the easy questions right. I've also got to have a lot of easy questions even at nationals, because guess what? Some teams, they're just at a different level of competition, and I've still got to be able to determine between 60th and 59th place. Am I coming to the North Carolina one? No, but I can tell you what, North Carolina is famous for top teams, and they are famous for hard tests. Okay. So download as many of them as you can. Okay. Now, if you got any specific questions, you can always email me, or better yet, have your coaches email me about specific questions. Is it normal to get below 90 at invitationals? Absolutely. It's normal to get below 90 at anything. If you're getting a 90 or above on a test, that means the test was probably too easy for you. Okay. But still, that's why you download all the tests off of Scioli and you're shooting for getting above a 90. And if you're always getting the same types of problems wrong, figure out what you're doing wrong. And actually, you can come to me, you can go to your coach, and that's what this forum is about. The number one thing I will tell you is that if you can simplify the problem, you're much more likely to get the problem right. Like if you noticed, I did a estimate and I knew that the answer for the resistance was going to be more than 20 but less than 30. And by doing that, when I did all the math, if I came up with something that said 35, I know I got it wrong. However, if I did something and the answer came out 15, I know I got it wrong too. If I came up with 28.4, it's reasonable. It made sense. New Jersey, great teams in New Jersey. I love your state director. She's a good friend of mine. We're friends on Facebook even. And I know New Jersey's got a lot of stuff going on. I would also say that if you're in New Jersey, look at what Pennsylvania's doing. Pennsylvania's doing some really cool stuff. They've got some of the best circuit lab tests out there. And again, if you can find them on the internet, all the better. For those of you that are going to nationals in circuit lab, Pennsylvania is the one who's going to be executing the circuit lab test at nationals. I'm actually going to be helping write the test, but I am not going to be executing it because my daughter graduates from high school on June 1st, which is nationals. So I won't be at nationals this year, which I'm really upset about because Cornell is a really cool campus. And you got Bill Nye the Science Guy and all that stuff going on at Cornell. I am going to be helping write the test. Okay. But Mr. Demos writes a much tougher test than me. Okay. So you better know how to calculate things. You better know things from a conceptual level much, much better. Okay. And his hands-on activities, he's expecting you to be able to look at a circuit or a device and then be able to calculate what the answer should be. And then your measurements, if they don't match, know why they don't match. He's the guy that taught me how to write a really good test. Okay, any other questions? So if you looked at the homework, remember I talked about like how to create a solenoid by wrapping wire around, okay? And then about how to put a core in it to make that solenoid or that electromagnet even stronger. Sometimes they'll use they'll usually use a lot longer piece of wire, okay? And then are there any other websites to find practice tests? Actually, I bet you there's tons of them, okay? There's this great thing called Google, and I highly recommend using it. The other thing is that if you go to scioli.org, they've actually got forums, and you can ask these questions on the forums, and people are more than happy to share old tests. But what I would do is do one test all the way through first and see where your trouble areas are. That's going to tell you where you need to beef up your binder. That's going to tell you the types of problems that you need to solve, okay? And when you do it, time yourself. Give yourself about 45 minutes the first time you take one of these tests, and it's going to scare the heck out of you, and you're going to run out of time, and that's great. Then you don't give yourself any credit for any of the questions you didn't answer. It also forces you to practice your test-taking ability. Answer the easy questions. If you remember on this problem here, okay, these were going to be fairly difficult questions, 1B, 1D, 1B, 1C, 1D. However, these guys were actually a little bit easier. So don't get stuck on these guys. Solve these. Also, look here. This color code one, you knew was an easy one because remember, you happen to have this in your binder. Okay? And so you knew that it was brown, green, and then you knew that you needed to multiply it times 10, which would be brown again. Okay? So that was an easy question to answer. Okay? Then I come over here, find the power dissipated by R7. Now, the power dissipated by R7, okay, if you look here, R7 is this one right here. Again, we have to solve these guys to figure out the current going through here so I can know either the voltage here, okay, or I could know the current. And in this case, I know it's probably going to be easier for me to figure out the current, okay? Now, let's look at this next problem. It's got two sources. It's got a current source and it's got a voltage source here, okay? Now, this one is drawn sort of goofy-like, okay? The ground is actually here. So this is by definition 0 volts here, okay? So it's 0 volts here, so it's minus 5 volts here. That's sort of a weird way to look at it, but it is minus 5 volts there. Okay, so what you're going to do is you're probably going to want to use superposition. And I'm going to want to solve it first with just the battery here. I take this one out, and that becomes an open circuit. And then it's a battery, if you will, with the 1.6 kilo ohms, 1.5 kilo ohms, and the 6.3 kilo ohms all in a series. And so that's a real easy problem to solve. Then I'm going to solve it with the current source all by itself. So when I solve it, this becomes a short. So I've got this current source here. And now I've got these two guys, which are easy to put in series. Okay. And then this guy here is now in parallel. So this 1.5 plus 1.5 is about 3.1 kilo ohms. It's in parallel with this 6.3. Okay. So this is going to end up being like about, it's going to be less than 3.1 kilo ohms. Okay. And so I've solved for that resistor. And now I can figure out how this current is split. Because guess what? This current here is split between this way around and this way around. Okay. And then it's all in series with this 500 ohm. So that one actually doesn't play into the splitting of the current. Then I can add those back together and solve for my voltages and my currents. Notice I didn't add the power back in because that goes as squared. I solve for the voltages and the currents and the resistances, and then I can put those back together when I want to do power. Do you need to know RC? You only need to know RC if you're division C. So RC is a division C topic only. But knowing what is capacitance and charge is division B. So for division B, you do not need to know how to do circuit analysis with capacitance and resistors. That's the good news. You will need to know it for division C. Okay? Now, they may give you a parallel plate with charges on it in division B and have you draw the electric field lines. And you know that they leave the positive and they go to the negative side. Oh, I'm so sorry, Mr. Pierce. I did not mean to make this thing so tough to read. Looks like most people are division B. All right, we're about at the end of our normal time. I'm willing to stay here longer if there's still more questions. I'm having a blast. By the way, I just did the Texas Coaches Clinic yesterday, and the Texas coaches are really doing a great job. And I think those teams of you that are in Texas are in good hands. You got to go soon. Okay. Any other questions before we sign off? Well, everyone have a wonderful Thanksgiving. I will be on next Sunday, but I realize not that many people will be able to join. But then we're going to do it every Sunday, okay? So take care, everyone.